All right, Chemistry 3101. This is Chapter 5, which deals with the topic of stereoisomerism. So you see the word isomer in here, in the word stereoisomerism, and I know that you all know what isomers are, right? Isomers are different compounds that have the same formula, but there's two types of isomers that we have to be concerned with as organic chemists. The first one are constitutional isomers. Now, I know that you already know what constitutional isomers are. Now, an example would be, what if I had this formula, C2H6O? There's actually two ways that I could connect those atoms, right? I could connect them together to make this compound. So I have a methyl group and an oxygen and another methyl group. This is called dimethyl ether. It's used as a propellant in things like aerosol cans, like whipped cream or spray paint, stuff like that. I don't know, cooking spray maybe. Anyhow, or you could arrange them like this to make this molecule, which is ethanol. Okay, and ethanol is the alcohol that's found in alcoholic beverages. It's also used as an additive in gasoline. But you know enough about intermolecular forces to know that these two compounds are very different, aren't they? Ethanol can participate in hydrogen bonding because it has a hydroxyl in it. Okay, so it's going to have a higher boiling point than dimethyl ether, which is a gas at room temperature, and ethanol is a liquid at room temperature. But again, they have the same constitution. They're made out of the same atoms. It's just the way that they're connected together that is different, right? It's the same thing as if, and maybe it's not exactly the same, but if I was to give everybody a budget, you know, and I said, everybody in class, I want you to go to Home Depot. We're all going to buy 4 sheets of plywood, you know, 100 2x4s and some shingles. And I want you to try and build something, you know, in a box of nails. And, you know, maybe one person would build a doghouse. Maybe another person would try to build, I don't know, what else you could build. What could you build? Maybe a chicken coop. Anyhow, but the idea is that it's made of the same atoms, but we end up with totally different molecules. Now, stereoisomers, which you can guess is going to be largely the focus of this chapter, are compounds that have the same molecular formula and the same constitution, which means they're connected in the same way, but have a different spatial arrangement of atoms. Let me give you an example before we move on and get into the real nitty gritty here. What if I had a cyclohexane molecule, okay, and if I had 2 methyl groups on it, okay? If I was to ask you to name that molecule based off of what you learned in chapter 4, maybe I could clean up that bond a little bit. Okay, if I was to ask you to name this molecule based on what you learned in chapter 4, you would say that's 1,2-dimethyl cyclohexane. And I would say you are 100% correct. Now, if I drew both of those methyl groups as wedges coming out towards you on the page, right, you would call that molecule cis 1,2-dimethyl cyclohexane. Why? Because the 2 methyl groups are both pointing up. They're on the same side of the molecule. Well, what if I drew this molecule? Okay, I put my cyclohexane, and I put one of the methyl groups coming up, but I put the other methyl group coming down. This would be called trans 1,2-dimethyl cyclohexane, wouldn't it? It would, right? Now, are these 2 molecules the same? No, they are not. But they are connected in the exact same way, right? They both have a 6-membered ring, and they both have 2 methyl groups attached. So their connectivity is the same, identical connectivity. What's the difference? It's the word space that's important here. It's the arrangement of atoms in space that is different. And this is something I kind of told you about in chapter 4. I said, imagine yourself, and I like to imagine myself shrunken down to the size of a molecule sometimes. I'm an organic chemist, can't help myself. Okay, imagine what you would see if you were standing here. You would see this methyl group right next to you. Whereas if it was the same you standing on the same methyl group, right, now you have to look down to see that methyl group. So clearly, the arrangement of the atoms in space is different, the cis and the trans 1,2-dimethyl cyclohexane. So we say that these molecules, the cis and the trans 1,2-dimethyl cyclohexane, are stereoisomers. They have the same molecular formula. They have the same constitution or connectivity, right? But they have a different spatial arrangement of atoms. So the 3-dimensional arrangement of the atoms is different, and that's what makes stereoisomers. So that's what I have shown here. Now we're just using Haworth projections for our cis and trans 1,2-dimethyl cyclohexane. So again, just to recap what we just covered, these 2 molecules, they both have the same connectivity. They both have 2 methyl groups in a 1,2 arrangement on that 6-membered ring, but they're stereoisomers. Why? Because the arrangement of atoms in space is different, okay? And we have to give them unique IUPAC names, don't we? We have to be able to differentiate between this molecule and this molecule. And that is why we use the prefixes cis and trans, right? If I go right back to where I started on the first slide, if I was to just write the structure here, okay, with no dashes or wedges, and if you're wondering, well, what is this, Mr. Dion? Is it cis or trans or is it a mixture? And I would say, not enough information provided, right? I haven't given you the information to tell you whether it is cis or trans or it's a mixture. So you don't really know if you just draw the structure like that. But in this chapter, we're going to draw molecules so that we do represent their 3D shape because it is important. Let me give you another example of stereoisomers. Okay? What if I had drawn this, condensed structure for you? What if I said CH3, a CH with a double bond to another CH and another CH3 like this? You'd say, well, I've got an alkene in here, okay? And that molecule is called 2-butene. It's neither here nor there, but that's the name of the molecule. It's called 2-butene. But the thing is, if you expand that structure and you draw a complete Lewis structure, you actually see that there's a couple of ways you can arrange the atoms in 2-butene in space, okay? You could either arrange it like this so that both of the methyl groups are on the same side. We call that cis 2-butene. And you could also arrange it so that the two methyl groups are on the opposite side of the double bond, and we call that trans 2-butene. Keep in mind that these are not in equilibrium. They never were. They never can be. Why? Because we do not have free rotation around a double bond. A double bond is rigid. If I grab my model kit here, I can do a very quick demo for you. Let me just switch over to my camera here for a split second. So I'm going to use my Feezer models to do this. I'll try not to break them. Here we go. But if I have 2-butene, so that's this molecule here, here's my double bond. You can see that my two methyl groups are cis. They're on the same side of the molecule. I cannot, watch, I cannot rotate the double bond. A double bond is rigid. It cannot be rotated. Yes, around a single bond, there's rotation, right? We can spin that all day long if you want. But in order for me to get the trans 2-butene, I've literally got to break a bond, which isn't going to happen spontaneously, and then I make the trans. Okay, the connectivity is the same in both molecules. CH3, CH, double bond, CH, CH3. Look, didn't change. We still have CH3, CH, double bond, CH, other CH3, but they cannot be interconverted, okay? So they're isomers, they have the same connectivity, but they have a different arrangement of atoms in space, don't they? And so they fall under that umbrella, that definition of stereoisomers. So cis and trans 2-butene are in fact stereoisomers of each other, all right? Same connectivity, but they're not identical. Again, they are stereoisomers. So that's what the definition of stereoisomers is. Well, the good news is that Chapter 5 has lots of points for class participation instead of me just lecturing on for hours and hours. So let's get into it, and let's see if we can identify these pairs of molecules as being either constitutional isomers, so compounds that have the same molecular formula but a different connectivity, identical, and that just means they're the same molecule, or if they are stereoisomers, which means they have the same connectivity, but they have a different arrangement of atoms in space. Let's start with these two up here in the top left corner. Could anybody tell me what the relationship between these would be? Absolutely, Jessica. These are identical, right? These are the exact same molecule. So, identical. Right? The connectivity of the two molecules in space is the same. What's the difference between these two? These are just two conformations, right? All I did was move the chair. Remember flipping the ring that we learned in Chapter 4 when we spent so much time talking about cyclohexane? This is just showing one conformation where I have the hydroxyl in the equatorial position, and in the other one, it's in the axial position. Exactly. I'm just drawing a smaller arrow on the bottom because we know that we have 1,3 diaxial interactions here, okay? But either way, this molecule is called cyclohexanol, so it's identical. All right, let's move down to the next two. I'll put them in a red box, these two here. What about these two? Could anybody tell me what these would be. Would these be stereoisomers, identical, constitutional? Yeah, I tend to agree. Yeah. Anybody else have an answer? So these two here with the two hydroxyls and the two hydroxyls here. All right, if I look at these two molecules, yeah, exactly, they're stereoisomers. You notice that this hydroxyl is pointing up, this hydroxyl is pointing up. So that means that these two hydroxyls are cis. So this is cis 1,2 cis 1,2 cyclohexane diol would be the name of the compound, but that's neither here nor there. But you notice here that this one is going up an axial and this one's going down. So obviously these two hydroxyls are trans to each other. The connectivity is still 1,2, right? 1,2, and if you want to label it this way, it doesn't matter. These are 1,2, this is 1,2. So the connectivity is the same, right? But they're stereoisomers because the arrangement of the atoms in space is different, right? So these are stereoisomers. Stereoisomers, absolutely. Let's move down to this one here. So these two, I'll put them in a blue box. This molecule is called THF, tetrahydrofuran. Anyhow, so I have tetrahydrofuran and I have this molecule, which is called butanone. I think I told you before, it's part of the flavor of buttered microwave popcorn. Yeah, absolutely. All my students nailed that one. They're constitutional isomers. So we'll put here constitutional isomers. What's the molecular formula? Both are C5, H1, 2, 3, 4, 5, 6, 7, 8. Right, both are C5H8O. There we go. Let's move up to this one here. Floating away here. What about these two that I have in the green area up here? Yeah, they're the exact same, right? These are the exact same molecule. They have the same connectivity. They're not stereoisomers. So we'll put here identical. And the last one. Let's try the last one. Got a couple of alkenes here. Excuse me. What about the last ones? Yeah, these ones would be, they're not identical. So they both are CH3, right? I'm starting over here with both of them. They both go CH3, CH, double bond, CH, CH2, CH3, right? They both have the same connectivity, but is the arrangement of the atoms in space the same? If I look at the two hydrogens here, right, these are trans to each other, right? And I'm talking about these two hydrogens, but these two hydrogens in this molecule are cis to one another. So these two are in fact stereoisomers. Stereoisomers, right? They have the same connectivity, but they have a different arrangement of the atoms in space. So again, trans and cis. So the first one would be called trans 2-pentene, and the second one would be called cis 2-pentene. All right, there we go. So that's a little practice on constitutional isomers, stereoisomers, identical structures. Let's try some more practice on cis-trans. So cis, trans, or neither. If I was to circle this alkene over here, could anybody tell me if that is cis or trans? And it's not a trick. Yeah, it's cis. Why? Because I have the two hydrogens that are on the same side of the double bond. So that is cis. What if I move down to this diol here? This guy. Also cis, yeah, because this one's going up and this one's going up, right? This one's up and axial. This one's up and equatorial, but they're both still up. So this one is cis. I'll just go over this one a little quicker because we already looked at an alkene, and I think we just looked at this alkene. This one is trans. The two hydrogens are on opposite sides. What about this one here? I think we already did this one too, didn't we? So this one is up and axial. This one is down and down and axial. So these two are, this molecule is obviously trans. Hey, okay, I got a question. This last one here, I'll put it in a, and you know how I always say, this isn't a trick question. This one is kind of a trick question. Is this one cis or trans? Or neither? Yeah, it's neither. Okay, it's neither. Because in order for something to be, let me explain why it's neither. So the answer is neither in this case. In order for something to be cis or trans, okay, that's an alkene, you've got to have two groups that are identical on the same side. So the reason we knew that this one in the top left was cis is because the two hydrogens are identical. The reason we knew this is trans is because the two hydrogens are identical. The problem with this molecule, the reason it's neither, is because here you have a methyl group, here you have a methyl group, and here you have a methyl group, and then here you have a hydrogen. So the methyl groups are all identical, right? There's three methyl groups, but hold on. This methyl group in the blue circle is trans to this one, but this methyl is cis to this one, so it's neither. There's no cis or trans. So the quick and dirty rule, the fast rule is this. Whenever you have an alkene and there's two groups on one of the carbons that are identical, if these groups are the same, okay, and it wouldn't matter if they're ethyl, methyl, propyl, isopropyl, butyl, hydrogens, chlorines, bromines, I don't care what it is, phenols, if they're the same, there is no cis or trans. Okay, whenever two groups on the carbon of the alkene, of one of the carbons in the alkene, whenever the two groups are identical on the same carbon, there is no cis or trans. It's impossible. Cannot exist. All right, there we go. Pretty good. All right, so the whole concept of cis-trans, it's only one type of stereoisomerism. There's a whole bunch of different types of stereoisomeric relationships. And in order for us to identify stereoisomers, other types, we've got to be able to identify what are called chiral molecules. So it's not chiral, it's chiral. So a chiral object is an object that is asymmetric, which you can simply think of that's not symmetrical, right? The asymmetric in organic chemistry, the way we define it is that it's non-superimposable on its mirror image. Okay, so if we make the mirror image, you can't plop it on top of it. Take a look at these two pairs of, these look like John Lennon's sunglasses, or John Lennon's glasses slash sunglasses, I don't know. Anyhow, if you look at this pair of glasses here, and you look at the mirror image, okay, if I was to take this pair, son of a gun, if I was to take this pair and try to plop them on top of this one, I could do it, right? So you would say that this pair of glasses is achiral. Again, let me review. The reason why this is achiral is because it would be superimposable upon its mirror image. If you were to take these glasses and flip them around, you could plop them on top and they would fit perfectly. The lenses are shaded in. Over here, when you poke out one of the lenses, the reason that this is a chiral object, this is a chiral pair of glasses, is because if you take these and you try to plop them on top of here, let me draw what you'd end up with. You'd have the two lenses like this, okay? But it would be this one that would be the shaded in one, and it doesn't, right? It doesn't fit on top of that. So give me a thumbs up if you follow me on the concept that this pair of glasses is achiral or symmetric because it is superimposable upon its mirror image, and the other pair of glasses is non-superimposable upon its mirror image. This is a really important concept, and you do have to be able to manipulate this pair of glasses in your mind and flip them around into this orientation and then try to superimpose them, and you see that they do not superimpose. Give me a thumbs up if you follow me on that one. Anybody with me on that? Okay, or stop me if you want me to review it. But before I started recording today, what I asked you was I showed you two molecules that were mirror images of each other. And I said that those two molecules, okay, were non-superimposable mirror images. So those molecules would have fallen under the umbrella of being chiral molecules, and I'll show you that example again. The reason why chirality is so important in molecules is that two chiral molecules, they're mirror images. They look, you know, if mirror images, I mean, they look identical, but they're not identical in their connectivity in space. And that means they're going to have a different pharmacology. That means they're going to elicit a different pharmacological response in the human body, which is very important. So visualizing mirror images and molecules and manipulating in 3D space to see if they're superimposable, it's very rare that I, highlight something in bold letters, but it can be very challenging. Okay, so Now, this is a point put in here by Dr. Klein, the author of our textbook. He thinks that it's critical that you have handheld models. Now, like I said, you can buy a model kit. Are my slides frozen? I'm moving them back and forth. Are my slides frozen? All right, if they're frozen, let's disconnect this. So go back into here.